Hello there, and welcome to another cosmic journey where the universe reveals its most puzzling secrets and distant mysteries drift into our neighborhood. Tonight, we're venturing into the realm of interstellar visitors, those enigmatic wanderers that have traveled unimaginable distances across the void between stars to grace our solar system with their presence. I'd love to know where you're watching from tonight and what draws you to these celestial mysteries, because here we are scattered across our pale blue dot, each of us gazing upward at the same stars, wondering what secrets they might hold. If this exploration into the cosmic unknown brings you a sense of wonder or helps you drift peacefully towards sleep, I'd be deeply grateful if you could give this video a like and perhaps subscribe it. LPS this little corner of cosmic curiosity, reach other stargazers who might find solace in the vastness above. Now, I do hope this isn't so fascinating that it keeps you wide awake. But if it does well, at least you'll have learned about some of the most extraordinary objects ever discovered in our solar system. So settle in. Let your thoughts wander among the stars. And let's begin our journey into the deep. Because somewhere in the darkness between worlds, between the familiar planets that orbit our sun and the distant stars that twinkle in our night sky, lies a story of visitors from realms so far away that their very existence challenges everything we thought we knew about our cosmic neighborhood. Imagine for a moment that you're sitting in your garden on a quiet evening watching the familiar dance of planets and satellites across the sky, when suddenly something appears that doesn't belong. Something that moves in a way that defies the predictable orbits you've come to expect, something that carries with it the dust and secrets of alien worlds. This isn't science fiction. This is the remarkable true story of three extraordinary objects that have fundamentally changed our understanding of what wanders through the cosmic sea and occasionally drops by for a visit. The first hint that our solar system might receive visitors from the great beyond came not from telescopes or satellites, but from the minds of astronomers who dared to imagine what might be possible in the vast spaces between stars. For decades, scientists theorized that objects ejected from distant planetary systems should occasionally wander into our cosmic backyard, like cosmic tumbleweeds blown by stellar winds across the galactic prairie. They calculated that these interstellar nomads should exist in significant numbers, drifting through the darkness, carrying with them the chemical signatures and physical characteristics of worlds we could never hope to visit. But theory is one thing, and discovery is quite another. It's a bit like knowing that rare birds must migrate through your area, while never actually spotting one, until that remarkable day in October 2017, when everything changed. A telescope in Hawaii, part of the Panoramic Survey Telescope and Rapid Response System known as PAN-STARRS, caught sight of something extraordinary moving across the sky in a way that no asteroid or comet from our solar system should move. The object, designated One-Eye 2017, U1, was given the Hawaiian name Oumuamua, meaning a messenger from afar, arriving first. And what a messenger it turned out to be. This wasn't just another space rock tumbling through the asteroid belt. This was our first confirmed visitor from another star system, a cosmic ambassador carrying secrets from realms so distant that light from their home stars might take centuries to reach us. Oumuamua was unlike anything astronomers had ever encountered. Its elongated shape, stretching perhaps 10 times longer than it was wide, made it appear almost like a cosmic cigar, or perhaps a shard of some unimaginably large crystalline structure. No known asteroid or comet in our solar system displays such extreme proportions. Most space rocks are relatively round or at least somewhat potato-shaped, but Oumuamua seemed to defy these conventional forms, as if it had been sculpted by alien forces or stretched by gravitational tides we could barely comprehend. As telescopes around the world turned their attention to this strange visitor, the true extent of its alien nature became apparent. Oumuamua was moving at tremendous speed, nearly 200,000 miles per hour. Far too fast to have originated anywhere within our solar system. The mathematics of celestial mechanics made it clear that this object had traveled through interstellar space for potentially millions of years before its chance encounter with our Sun. Its trajectory traced a hyperbolic path that would carry it past our star and back out into the cosmic void, never to return. But speed and shape were just the beginning of Oumuamua's mysteries. As astronomers continued their observations, they noticed something that challenged their understanding of how celestial objects behave. The visitor was accelerating in a way that couldn't be explained by the gravitational influence of the Sun and planets alone. It was as if some invisible force was giving it a gentle push, propelling it faster along its outbound journey. In our solar system, when objects accelerate unexpectedly, it's usually because they're comets releasing gas and dust as they heat up near the Sun. This outgassing creates a rocket-like effect that can alter an object's trajectory. But Oumuamua showed no signs of such activity. No glowing coma of vaporized ice. No streaming tail of dust and debris. It appeared to be accelerating like a comet while looking like an asteroid, a contradiction that sparked heated debates in astronomical circles. The mystery deepened when scientists realized that Oumuamua was tumbling through space in a complex rotation that caused its brightness to vary dramatically as different surfaces reflected sunlight back toward Earth. This tumbling motion suggested that the object might have experienced violent collisions or gravitational encounters during its long journey through interstellar space. Each rotation revealing different facets of its enigmatic surface. Some researchers proposed exotic explanations for Oumuamua's behavior, suggesting it might be composed of unusual materials or even represent technology from an advanced civilization. While such ideas captured public imagination, the scientific community remained focused on finding natural explanations for the object's strange characteristics. The debate raged for years as astronomers struggled to reconcile Oumuamua's comet-like acceleration with its asteroid-like appearance. Then in 2019, just 2 years after Oumuamua's discovery, another interstellar visitor arrived to shake up our understanding. Once again, this time an amateur astronomer in Crimea named Gennady Borisov spotted something unusual moving across the night sky. His careful observations and immediate recognition that the object was behaving strangely led to the discovery of 2I Borisov, the second confirmed interstellar object, and the first that clearly displayed cometary characteristics. Unlike the enigmatic Oumuamua comet, Borisov behaved exactly as astronomers expected an interstellar comet should behave. It developed a bright coma of gas and dust as it approached the Sun. It displayed the classic signs of outgassing that create the beautiful tails we associate with comets, and its composition, when analyzed spectroscopically, revealed familiar chemical signatures that matched comets from our own solar system. Borisov's discovery provided both relief and new puzzles for astronomers. Relief because it confirmed that interstellar comets could behave in predictable ways, validating decades of theoretical work about how such objects should appear. Puzzles because its composition, while comet-like, showed some unusual characteristics, including an unexpectedly high concentration of carbon monoxide and evidence of materials that had formed under extremely cold conditions. The comet's pristine nature became apparent as detailed observations revealed that Borisov had likely never passed close to a star before its encounter with our Sun, making it an undisturbed relic of the cloud of gas and dust from which it originally formed. This pristine quality made Borisov extraordinarily valuable to scientists, as it offered insights into the original composition of materials from another stellar system, a cosmic fossil preserving ancient chemistry from the early days of a distant planetary system. As Borisov continued its journey through our solar system, telescopes captured images of the comet, fragmenting as pieces of its nucleus broke away under the stress of solar heating. This fragmentation provided unique insights into the internal structure of interstellar comets, revealing that despite surviving journeys across vast distances, these objects could be surprisingly fragile when exposed to the intense radiation environment near a star. The discoveries of Oumuamua and Borisov established that interstellar objects were not just theoretical possibilities, but real visitors that we could study and learn from. They opened a new window into the processes operating in distant planetary systems and demonstrated that the space between stars was not empty, but populated by countless wandering worlds, ejected from their birth systems and set adrift in the cosmic sea. But the story of interstellar visitors was far from complete, because just when astronomers thought they were beginning to understand these cosmic wanderers, another surprise was hurtling toward us through the darkness between stars, carrying with it mysteries that would challenge everything we thought we knew about the age and origins of objects drifting through our galaxy. In July 2025, the Atlas Survey telescope in Chile detected something moving against the backdrop of stars, with a trajectory that immediately caught the attention of astronomers around the world, initially given the rather mundane designation A11PL3s. This new object quickly revealed itself to be anything but ordinary, as rapid follow-up observations confirmed what the initial data had suggested. We were witnessing the arrival of our third confirmed interstellar visitor, designated 3I Atlas, where the 3I stands for Third Interstellar. This newest cosmic wanderer brought with it a set of characteristics that pushed the boundaries of what astronomers thought possible for objects traveling between the stars. The numbers alone were staggering. Atlas was racing through our solar system at roughly 130,000 miles per hour, making it the fastest moving visitor ever recorded. But speed was just the beginning of its extraordinary nature. The orbital calculations revealed an eccentricity of 6.2, a number that represents the most extreme hyperbolic trajectory ever measured for any object in our solar system. To put this in perspective, Oumuamua had an eccentricity of about 1.2, while Borisov measured 3.6. Atlas was operating on an entirely different scale, suggesting it had originated from much farther away or under vastly different conditions than its predecessors. As telescopes around the world focused on this latest arrival, the true magnitude of its significance began to emerge. Preliminary analysis suggested that Atlas might be far older than anything previously encountered in our solar system. Calculations indicated it could be over 7 billion years old, making it potentially 3 billion years older than our Sun and planets. If confirmed, this would make Atlas not just an interstellar visitor, but a genuine time traveler, carrying with it materials and chemistry from an epoch when our solar system didn't even exist. The implications of such ancient origins are profound. Atlas may have formed in a region of our galaxy called the thick disk, a component populated by older stars with different chemical compositions than the younger stars found in our Sun's neighborhood. These ancient stellar systems formed when the universe contained fewer heavy elements, meaning Atlas could provide insights into planetary formation processes, operating under conditions vastly different from those that created our own solar system. Size estimates for Atlas have proven challenging, with different observation methods yielding dramatically different results. Some measurements suggest a nucleus less than 6 kilometers in diameter, while others indicate it could be as large as 46 kilometers across. If the larger estimates prove correct, Atlas would possess 1 million times more mass than Borisov, making it a genuine giant among interstellar objects. The uncertainty in size measurements reflects one of the fundamental challenges in studying these distant visitors. When a comet develops an active coma of gas and dust, the bright envelope surrounding the nucleus makes it extremely difficult to determine where the solid object ends and the surrounding material begins. It's rather like trying to measure the size of a streetlight through thick fog. The light is there, but the source becomes impossible to pin down precisely. What we can observe with greater certainty is Atlas's evolving appearance as it approaches the Sun. Multiple telescopes have detected a distinctly reddish coloration in its coma, indicating the presence of dust and organic compounds similar to those found in certain types of asteroids, rich in carbon-based materials. This reddish hue has been growing more pronounced as Atlas becomes more active, suggesting that heat from our Sun is liberating materials from deep within the comet's nucleus. Spectroscopic analysis has revealed a composition that includes organic compounds, silicates carbonate minerals, and significant amounts of water ice. This mixture of materials tells a story of formation in an environment where both rocky and icy components could coexist, suggesting Atlas originated in the outer reaches of its home planetary system, where temperatures were cold enough to preserve volatile compounds over billions of years. The detection of these organic materials is particularly intriguing, as they may represent complex carbon chemistry that developed under conditions very different from those in our solar system. Studying these compounds could provide insights into whether the basic building blocks of life as we know it are universal features of planetary formation, or whether different stellar environments produce entirely different chemical pathways. As Atlas continues its journey through our solar system, astronomers are racing to gather as much data as possible before this ancient wanderer disappears back into interstellar space. The window of opportunity for detailed study is limited, measured in months rather than years, making every observation precious in building our understanding of these remarkable cosmic time capsules. The 3 interstellar visitors we've encountered so far, Oumuamua, Borisov, and now Atlas, represent just the tip of a vast iceberg of objects wandering through the galaxy. Theoretical calculations suggest that at any given moment, thousands of interstellar objects may be passing through the outer reaches of our solar system invisible to our current detection methods, because they're too small, too distant, or too inactive to produce the signatures our telescopes can detect. Recent estimates indicate that several interstellar objects similar in size to Oumuamua pass inside Earth's orbit each year, while tens of thousands may be traversing the region inside Neptune's orbit at any given time. These numbers suggest that interstellar space is far from empty, but rather populated by a vast diaspora of objects ejected from planetary systems throughout our galaxy's history. The ejection process itself tells a fascinating story of planetary system dynamics. Computer simulations suggest that during the formation of planetary systems, gravitational interactions between planets and their parent stars result in the ejection of far more objects than are retained in stable orbits. Some models indicate that for every comet that ends up in a system's equivalent of our Oort cloud, 3 to 100 others are flung into interstellar space to begin wandering journeys that may last billions of years. This cosmic diaspora means that the objects we've detected represent ambassadors from planetary systems scattered across our local region of the galaxy, each carrying with it chemical and physical information about conditions in stellar environments we may never be able to visit directly. They are, in essence, our only means of directly sampling materials from other worlds beyond our solar system. The discovery rate of these objects is expected to increase dramatically in the coming years. As new survey telescopes come online, the Vera Rubin Observatory, currently under construction, promises to revolutionize our ability to detect faint, fast-moving objects with its wide field of view and sensitive detectors, potentially discovering dozens or even hundreds of interstellar visitors during its planned decade-long survey. This increased detection capability will transform interstellar object research from the current situation of analyzing individual rare specimens to conducting statistical studies of entire populations. Such studies could reveal patterns in the types of objects ejected by different kinds of stellar systems, provide insights into the frequency of planetary formation throughout our galaxy, and perhaps even identify objects that originated from specific nearby star systems. The chemical signatures preserved in these ancient wanderers also offer unique opportunities to study stellar nucleosynthesis and chemical evolution on galactic scales. Elements heavier than hydrogen and helium are created in the nuclear furnaces of stars and distributed through space when those stars die. Objects like Atlas that formed billions of years ago carry with them the chemical fingerprints of stellar populations that may no longer exist, providing windows into epochs of galactic history that we cannot observe directly. Each of these interstellar visitors also challenges our understanding of what constitutes normal in the cosmos. For most of human history, our perspective on planetary systems was necessarily limited to our own. The 8 planets orbiting our Sun in relatively circular paths, the asteroid belt nestled between Mars and Jupiter, the Kuiper belt beyond Neptune, filled with icy remnants from our system's formation. This was our template for how things should work, but Oumuamua, Borisov, and Atlas have shown us that the universe operates on scales and timelines that dwarf our local experience. These objects have witnessed the birth and death of stars traveled through regions of space where the nearest stellar neighbor might be dozens of light years away, and survived conditions of cold and radiation that would obliterate most materials we encounter on Earth. The loneliness of their journeys is almost incomprehensible. Imagine an object drifting through the void for millions of years with no nearby star to warm its surface, no gravitational anchor to provide stability. Just the endless night between worlds, punctuated perhaps by the distant glow of galaxies so far away they appear as mere pinpricks of light. The fact that these objects maintain their structural integrity over such vast timescales speaks to processes of formation and evolution that we're only beginning to understand. Atlas, in particular, with its potentially ancient origins, offers a glimpse into conditions that existed when our galaxy was young, and the first generation of stars was beginning to forge the heavy elements that would eventually become planets and life. The chemistry locked within its nucleus may preserve signatures from an epoch when the universe itself was fundamentally different, when stellar formation rates were higher, when the interstellar medium had a different composition, when the very processes that create planetary systems were still being refined through cosmic trial and error. The reddish coloration observed in Atlas's coma as it approaches our Sun tells its own story of survival and transformation. The organic compounds responsible for this hue have endured not just the formation process in its home system, but eons of exposure to cosmic radiation, high-energy particles from distant supernova and other violent cosmic events that would have gradually altered the chemical structure of surface materials. This process of space weathering operates like an incredibly slow form of cosmic archaeology. Each impact from a microscopic dust grain, each interaction with a cosmic ray particle leaves its mark on these wandering objects, creating a record of their journey that can be read by those who understand the language of spectroscopy and chemical analysis. The fact that Atlas shows signs of active outgassing as it nears our Sun, despite its incredible age, demonstrates the remarkable preservational power of the deep cold. Between stars' temperatures in interstellar space hover just a few degrees above absolute zero, cold enough to freeze virtually any known substance into a crystalline solid that can remain stable for geological timescales. This cosmic deep freeze has essentially mummified Atlas, preserving ancient chemistry in a state that allows us to study it billions of years after its formation. The evolving composition of Atlas's coma as solar heating begins to liberate different materials from its nucleus provides a kind of real-time stratigraphy, allowing astronomers to peer deeper into its structure. As each layer vaporizes, the changing chemistry tells the story of how conditions varied during the object's formation, perhaps reflecting different epochs in its home system's evolution, or different regions, where various materials condensed from the primordial disk. Studying these layered compositions is rather like reading tree rings. Except instead of annual growth patterns, we're observing the chemical fingerprints of ancient stellar environments. Each spectral line revealing the presence of elements forged in long-dead stars. Each molecular signature telling us about temperatures, pressures, and chemical processes operating in a planetary system that may have ceased to exist eons before our own Sun began to shine. The detection of water ice within Atlas, despite its extreme age and long exposure to the harsh environment of interstellar space, demonstrates just how effectively the cold of deep space can preserve even volatile materials. This ice likely formed through direct condensation from the gas and dust cloud that gave birth to Atlas's home system, capturing within its crystalline structure the isotopic ratios and chemical impurities that characterize that ancient environment. When this ancient ice begins to sublime as Atlas approaches our Sun, it releases not just water vapor, but a complex cocktail of gases that were trapped within the ice matrix during formation. These trapped gases serve as time capsules, carrying with them the atmospheric signatures of a world that may have been destroyed by stellar evolution or planetary collisions billions of years ago. The organic compounds detected in Atlas's spectrum raise profound questions about the universality of carbon-based chemistry throughout the galaxy. These complex molecules formed under conditions vastly different from those that created similar compounds in our own solar system. Yet their presence suggests that the fundamental processes that create the building blocks of life may be universal features of planetary formation, regardless of when or where that formation occurs. The implications extend beyond mere chemistry to touch on some of the deepest questions we can ask about our place in the universe. If objects like Atlas carry organic compounds formed in ancient stellar systems, it suggests that the chemical pathways leading to biological complexity may have been operating throughout our galaxy's history, perhaps creating the conditions for life in environments and epochs. We're only beginning to imagine. The extreme velocity and orbital characteristics of Atlas also provide clues about the violent processes that ejected it from its birth system to achieve such tremendous speed. Relative to our Sun, Atlas must have experienced gravitational encounters of extraordinary intensity, perhaps a close approach to a massive star, or passage through a region where multiple stellar systems were interacting gravitationally. These ejection events represent some of the most dramatic moments in a planetary system's evolution, when the delicate gravitational balance that keeps objects in stable orbits is suddenly disrupted by external forces. The fact that Atlas survived such encounters intact while still retaining its volatile materials speaks to either remarkable structural strength or perhaps simply cosmic luck in avoiding the most destructive aspects of whatever cataclysm set it wandering. The study of ejection dynamics through objects like Atlas also informs our understanding of how planetary systems evolve over cosmic time. Computer simulations suggest that most systems go through periods of instability during their formation, when massive planets migrate inward or outward, disrupting the orbits of smaller bodies and flinging countless objects into interstellar space. Our own solar system likely experienced such periods of chaos during its youth, with evidence suggesting that the giant planets may have migrated significantly from their original positions during the first few 100 million years after formation. This migration would have scattered objects throughout the outer solar system and beyond, perhaps contributing our own share of wanderers to the galactic population of interstellar objects. The realization that we live in a galaxy where countless objects are constantly being exchanged between stellar systems fundamentally changes how we think about planetary formation and evolution, rather than isolated systems. Developing in splendid isolation, we now recognize a vast network of material exchange, where the detritus of one system's formation becomes the raw material for discoveries in another. This cosmic recycling operates on timescales so vast that objects ejected during our galaxy's youth are only now arriving in our neighborhood, carrying with them information about stellar and planetary processes that operated when the Milky Way itself was young and actively forming new stars at rates far higher than we observe today. The detection and study of interstellar objects like Atlas also represents a new frontier in astrobiology, not because these objects are likely to harbor life themselves, but because they provide insights into the distribution and evolution of the chemical building blocks that make life possible by sampling materials from diverse stellar environments. We can begin to map the chemical evolution of our galactic neighborhood and understand how the ingredients for biological complexity have been distributed through space and time. The organic compounds found in these wandering objects may represent a form of panspermia, not the transfer of actual living organisms between worlds, but the distribution of the complex chemistry that serves as life's foundation. If such compounds are common in interstellar objects, they could seed new planetary systems with the molecular diversity needed for biological evolution to begin each new interstellar visitor. We detect adds another piece to this vast cosmic puzzle. Atlas, with its extreme age and pristine preservation, offers a particularly valuable glimpse into the deep past, while future discoveries may reveal objects from more recent stellar environments, allowing us to trace the evolution of planetary formation processes across cosmic history. The technological challenges of studying these fleeting visitors continue to drive innovation in astronomical instrumentation and techniques. The brief windows of opportunity for detailed observation demand rapid response capabilities and sophisticated instruments that can extract maximum information from limited observing time. The development of automated detection systems like the Atlas survey that discovered our latest visitor represents a fundamental shift in how we monitor the sky for unusual objects. These systems can process vast amounts of data in real time, identifying objects with unusual motions or characteristics that warrant follow-up observation by larger, more specialized telescopes. As our detection capabilities continue to improve, we can expect the discovery rate of interstellar objects to increase exponentially, transforming these rare curiosities into a regular part of astronomical research. The Vera Rubin Observatory. When it begins, operations promises to detect dozens or potentially hundreds of such objects each year, turning the study of interstellar visitors from an exotic specialty into a mainstream astronomical discipline. This transformation will enable statistical studies that can reveal patterns in the types of objects ejected by different stellar environments, the relationship between stellar mass and the characteristics of ejected materials, and perhaps even the identification of objects that originated from specific nearby star systems, whose properties we can observe directly. The prospect of linking specific interstellar objects to their stellar origins opens fascinating possibilities for comparative planetology. Imagine identifying an object that originated from Proxima Centauri, our nearest stellar neighbor, and comparing its composition to materials from other nearby systems. Such studies could reveal how stellar mass, metallicity, and age influence the types of objects that form in different environments. The chemical fingerprints preserved in these ancient wanderers also serve as cosmic chronometers, carrying isotopic signatures that can reveal not just when they formed, but under what conditions different radioactive isotopes decay at known rates, creating natural clocks that have been ticking away during these objects' journeys through space. By measuring the ratios of parent and daughter isotopes in materials from Atlas and future discoveries, we can begin to piece together timelines of galactic chemical evolution. This isotopic archaeology becomes particularly powerful when combined with observations of the stellar populations in different regions of our galaxy. The thick disk region from which Atlas likely originated contains stars with distinctly different chemical signatures than those found in our Sun's local neighborhood. By studying objects from various galactic regions, we can map how the distribution of elements has changed over cosmic time. The preservation of such ancient materials in Atlas also raises intriguing questions about the limits of stability in interstellar space. While the cold of the cosmic void provides excellent preservation conditions, these objects are not entirely isolated during their wandering journeys. They encounter cosmic ray particles, stellar winds from distant stars, and occasionally gravitational perturbations from passing stellar systems. Each of these interactions leaves its mark, creating a kind of environmental record of the regions through which these objects have traveled. Cosmic ray exposure can alter surface chemistry, creating new compounds and isotopic signatures that reveal how long an object has been wandering through space. The absence or presence of certain decay products can tell us whether an object took a direct path from its origin or meandered through regions of varying radiation intensity. The gravitational history of interstellar objects can also be inferred from their physical characteristics. Objects that have experienced close encounters with massive stars may show signs of tidal stress, elongation, or fragmentation, while those that have traveled through relatively empty regions of space may preserve more pristine shapes and structures. Atlas, with its extreme orbital characteristics, suggests a particularly violent ejection event that imparted tremendous energy to the object. The mathematics of orbital mechanics indicate that achieving such high velocities requires either a very close encounter with a massive object or passage through a region where multiple gravitational sources were interacting simultaneously. Such extreme ejection events might occur during the formation of binary star systems, when two massive stars settle into orbit around each other. Their gravitational dance can scatter smaller objects throughout the surrounding region, like cosmic billiard balls. These scenarios could explain not only Atlas' high velocity, but also its ancient age if it was ejected during the early phases of stellar system formation, when such violent interactions were more common. The study of ejection mechanisms through interstellar objects also informs our understanding of planetary system architecture. The fact that we observe objects with such diverse characteristics suggests that planetary systems throughout our galaxy span a much wider range of configurations than we might have expected. Based solely on our own solar system, some systems may be dominated by close binary stars, creating chaotic gravitational environments where stable planetary orbits are rare and ejection events frequent. Others might contain massive planets in highly elliptical orbits that periodically disrupt the trajectories of smaller bodies, sending waves of objects into interstellar space during each close approach to their parent star. The diversity we observe in interstellar visitors hints at the remarkable variety of planetary formation outcomes possible under different stellar conditions. Each object carries with it the signature of its birth environment, providing clues about the range of processes that can occur during the assembly of worlds around other stars. The detection of complex organic compounds in these wandering objects also raises profound questions about the role of interstellar chemistry in biological evolution. The harsh radiation environment of space might be expected to break down complex molecules over the timescales involved in interstellar journeys. Yet we continue to find evidence of sophisticated carbon chemistry in these ancient travelers. This preservation of organic complexity suggests either that these compounds are more stable under space conditions than previously thought, or that they are continuously being created through interactions between simpler molecules and the radiation environment itself. Some theoretical models propose that cosmic ray bombardment might actually drive the formation of complex organics in icy materials, creating a kind of cosmic chemistry laboratory, operating over geological timescales. If this cosmic chemistry is indeed creating biological precursors during interstellar journeys, it would mean that the building blocks of life are not just formed in planetary systems, but continue to evolve and complexify during the wandering phase between stars. This process could serve as a mechanism for distributing increasingly sophisticated chemistry throughout the galaxy, ensuring that new planetary systems have access to the molecular diversity needed for biological evolution. The implications extend to our search for life beyond Earth. If complex organics are common in interstellar objects, and these objects occasionally impact planetary surfaces, they could serve as delivery mechanisms, bringing sophisticated chemistry to worlds that might otherwise lack the conditions necessary for generating such compounds locally. The bombardment of early Earth by comets and asteroids is thought to have played a crucial role in delivering water and organic compounds to our planet. If some of those impactors were interstellar objects carrying chemistry from distant stellar environments, they may have seeded Earth with molecular diversity that contributed to the emergence of life. Studying the organic inventory of current interstellar visitors like Atlas provides insights into what kinds of chemistry might have been delivered to Earth during its formation. Epoch, the compounds we detect in these objects today, may be similar to those that arrived on our world billions of years ago, carried by earlier generations of wandering objects. The timing of such deliveries could also be crucial for biological evolution objects arriving during a planet's formation phase when surfaces are still molten, would have their organic cargo destroyed by extreme temperatures. But those arriving later after surface conditions have stabilized could deposit their chemical treasures intact. The study of interstellar object chemistry also informs our understanding of how molecular complexity emerges in different environments. The conditions under which Atlas formed over 7 billion years ago were vastly different from those operating today. The early universe contained fewer heavy elements, and stellar formation processes may have operated under different physical regimes. Yet the organic compounds we detect in Atlas suggest that the fundamental processes leading to chemical complexity were already operating during this ancient epoch. This provides important constraints on theories of chemical evolution and suggests that the pathways to biological complexity may be more robust and universal than previously thought. The preservation of such ancient chemistry also offers unique opportunities to study molecular evolution across cosmic time. By comparing the organic inventories of objects with different ages, we can begin to trace how the complexity and diversity of interstellar chemistry has changed as our galaxy has evolved. Objects from the galactic thick disk, like Atlas, represent one end of this temporal spectrum, carrying chemistry from an epoch when the universe was young and stellar. Nucleosynthesis was just beginning to enrich the interstellar medium with heavy elements. Future discoveries of objects from more recent stellar environments will fill in the intermediate stages, allowing us to construct a timeline of cosmic chemical evolution. This temporal sampling of interstellar chemistry becomes particularly powerful when combined with observations of stellar populations in different galactic regions. By correlating the chemical signatures of interstellar objects with the properties of stars in their likely regions of origin, we can begin to understand how stellar evolution drives the chemistry available for planetary formation. The metallicity of stars, the abundance of elements heavier than hydrogen and helium, varies significantly across different galactic populations. Stars in the thick disk, like those that may have given birth to Atlas, formed when the galaxy was metal-poor, containing much lower abundances of the heavy elements crucial for rocky planet formation. Studying objects from such metal-poor environments provides insights into how planetary formation proceeds under these different chemical conditions. The composition of Atlas may reveal whether rocky materials can still condense efficiently from gas clouds with low heavy element abundances, or whether such environments favor the formation of different types of objects entirely. The size estimates for Atlas, ranging from less than 6 kilometers to potentially over 40 kilometers in diameter, highlight another fundamental challenge in studying these distant visitors. The uncertainty in these measurements reflects the difficulty of separating the solid nucleus from the surrounding coma of gas and dust that develops as the object approaches our sun. This observational challenge becomes more than just a technical problem. It affects our ability to understand the size distribution of interstellar objects, and by extension the processes that create and eject them from their birth systems. If Atlas is indeed as large as some estimates suggest, it would represent a fundamentally different class of interstellar object than the relatively small bodies we have previously encountered. Large interstellar objects, like a massive Atlas, would have different survival characteristics. During their wandering journeys, their greater gravitational binding would make them more resistant to tidal disruption during close encounters with stars, while their larger surface area would make them more susceptible to erosion by cosmic ray bombardment and micrometeorite impacts. The discovery of such large interstellar objects would also have implications for impact hazards in planetary systems. While the probability of collision between any specific interstellar object and a planet is extremely low, the consequences of such an impact would depend strongly on the size and velocity of the incoming object. A massive high-velocity interstellar impactor could deliver tremendous energy to a planetary surface, potentially affecting global climate and biological evolution. The study of cratering records on planetary surfaces throughout our solar system may need to be reinterpreted in light of potential contributions from interstellar impactors. The chemical signatures left by such impacts might be detectable in ancient rock formations, providing another window into the history of interstellar object encounters with our world. The extreme velocity of Atlas, over 130,000 miles per hour, also sets it apart from typical solar system objects and even from previous interstellar visitors. This tremendous speed affects every aspect of how we study the object, from the observational challenges of tracking something moving so rapidly across the sky, to the theoretical implications of what could accelerate an object to such velocities. High-velocity impacts with interstellar dust and gas during Atlas' long journey would have gradually eroded its surface, creating a kind of cosmic sandblasting effect that could alter surface chemistry and expose deeper layers of material. This process might explain some of the evolving spectral characteristics observed as Atlas approaches our Sun, with each layer of eroded material revealing different aspects of its composition and formation history. The aerodynamic effects of moving through even the tenuous interstellar medium at such speeds could also influence an object's shape and surface properties over cosmic timescales. The pressure from interstellar hydrogen and helium, while incredibly weak, could gradually sculpt surface features and perhaps contribute to the unusual elongated shapes observed in some interstellar objects. The detection of these high-velocity objects also pushes the limits of our current observational capabilities. Tracking something moving at over 130,000 miles per hour requires extremely precise measurements and rapid telescope response times. The brief observational windows available before such objects disappear back into interstellar space demand coordination between multiple observatories and sophisticated automated detection systems. The development of next-generation survey telescopes, specifically designed to detect fast-moving objects, will be crucial for expanding our catalogue of interstellar visitors. The Vera Rubin Observatory, with its wide field of view and rapid survey cadence, represents a major advancement in this capability, promising to detect dozens or potentially hundreds of interstellar objects during its operational lifetime. This dramatic increase in detection rates will transform our understanding of these objects from isolated case studies to statistical populations, allowing us to address fundamental questions about the frequency of ejection events, the typical sizes and compositions of wandering objects, and the relationship between stellar system properties and the characteristics of their ejected materials. The coordination required for rapid follow-up observations of newly discovered interstellar objects also drives innovation in astronomical communication and data sharing systems. When Atlas was first detected, the astronomical community mobilized telescopes around the world within hours, demonstrating the kind of rapid response capability needed to maximize the scientific return from these fleeting visitors. This global coordination becomes even more critical as detection rates increase with multiple interstellar objects potentially visible simultaneously, requiring careful prioritization of observational resources and sophisticated scheduling algorithms to ensure that the most scientifically valuable targets receive adequate study. The international nature of interstellar object research also highlights the importance of collaborative approaches to understanding these cosmic wanderers. Objects that may have formed in stellar systems hundreds of light-years away and traveled for millions of years through interstellar space represent a shared heritage for all humanity, transcending national boundaries and political divisions. The study of objects like Atlas connects us to the broader galactic community, revealing our solar system as just one node in a vast network of stellar systems that have been exchanging materials and information for billions of years through the medium of these wandering ambassadors, each carrying within its ancient structure the story of worlds we may never visit but can now sample directly. As we continue to develop our capabilities for detecting and studying interstellar visitors, we stand on the threshold of a new era in astronomy, one where the chemistry and physics of distant worlds become directly accessible through the analysis of these cosmic time capsules. The secrets locked within objects like Atlas represent keys to understanding not just the history of our own galactic neighborhood, but the fundamental processes that shape planetary systems throughout the universe. The journey of discovery that began with Oumuamua's puzzling acceleration continued through Borisov's familiar yet exotic chemistry, and now reaches new heights with Atlas' ancient origins and extreme characteristics. Wandering worlds and their role in the cosmic story, each visitor has expanded our understanding while raising new questions about the nature of the complex web of gravitational interactions that populate our galaxy with these remarkable nomads. As we delve deeper into the implications of these discoveries, we begin to realize that what we once considered empty space is actually a bustling highway of ancient travelers, each carrying stories from worlds beyond imagination. The sheer number of these objects estimated to be wandering through our cosmic neighborhood at any given moment paints a picture of a galaxy far more dynamic and interconnected than we ever dreamed possible. Current models suggest that at this very moment, thousands of objects, similar to Atlas, are silently drifting through the outer reaches of our solar system, invisible to our current detection methods, but present nonetheless like ghost ships sailing through the cosmic dark. This hidden population represents one of the greatest observational challenges in modern astronomy. How do you find something that emits no light of its own, reflects only the faintest traces of starlight, and moves against a background of distant stars, with trajectories that may not follow the predictable patterns we associate with solar system objects? The answer lies in the patient, systematic monitoring of vast areas of skywatching for the subtle movement that betrays the presence of these wandering visitors. The Atlas survey system that detected our most recent visitor represents exactly this kind of patient vigilance. Automated telescopes scanning the heavens night after night, comparing images taken hours or days apart to identify anything that has moved against the stellar background. It's a cosmic game of spot, the difference played out on a scale that encompasses the entire visible sky, with computers serving as tireless sentries, watching for the telltale signs of motion that might indicate another messenger from the deep. But detection is only the first step in understanding these objects. Once identified, they become targets for the most sophisticated instruments astronomers can bring to bear: spectroscopes that can analyze their chemical composition. By examining the light, they reflect photometers that measure subtle changes in brightness as they tumble through space, and imaging systems that can reveal details of their shape and surface features. Each observation must be carefully timed and precisely executed, because the window of opportunity is limited by the object's trajectory and velocity. Atlas racing through our solar system at over 130,000 miles per hour allows only a brief period for detailed study before it disappears back into the interstellar void. This creates a sense of urgency that permeates every aspect of interstellar object research, a race against time to extract every possible piece of information before the visitor vanishes. The international collaboration required for these studies has created a new model for astronomical research. When Atlas was first detected, observatories around the world immediately began coordinating their efforts. Telescopes in Chile captured initial spectra, while instruments in Hawaii tracked its motion, and facilities in space provided additional wavelength coverage that cannot be obtained from Earth's surface. This global response demonstrates how the study of interstellar objects transcends traditional boundaries in astronomy. These visitors belong to no single nation or institution. They are emissaries from the galaxy itself, requiring the combined efforts of the entire astronomical community to unlock their secrets. The data flows freely between observatories as scientists race to understand each new discovery before it slips away into the darkness. The technological demands of studying these fleeting visitors continue to drive innovation in astronomical instrumentation. New detector technologies that can capture more light in shorter exposure times, adaptive optics systems that can maintain sharp focus on rapidly moving targets, and automated analysis software that can quickly process vast amounts of data to identify the most important characteristics of each object. The development of space-based observatories specifically designed to study interstellar objects represents the next frontier. In this field, telescopes positioned beyond Earth's atmosphere can observe these visitors across the full electromagnetic spectrum without interference from our planet's atmosphere, while their location in space provides stable platforms for the long-duration observations needed to track objects across their entire passage through the inner solar system. The James Webb Space Telescope, with its unprecedented infrared sensitivity, has already begun contributing to interstellar object research, providing detailed thermal observations that reveal information about surface composition and internal structure that cannot be obtained through visible light alone. Future dedicated missions may even attempt to intercept interstellar visitors, with spacecraft equipped to conduct detailed in situ analysis. The concept of intercepting an interstellar object with a spacecraft presents extraordinary technical challenges. These visitors approach our solar system with such high velocities that matching their speed and trajectory requires propulsion capabilities at the very limits of current technology. Yet the scientific rewards of such a mission would be immense, providing direct samples of materials from another star system for analysis in terrestrial laboratories. Several mission concepts have been proposed, ranging from high-speed flyby encounters that would capture images and spectra during brief close approaches to more ambitious rendezvous missions that would attempt to pace alongside an interstellar visitor. For extended periods of observation, the engineering challenges are formidable but not insurmountable, representing the kind of ambitious goals that drive technological advancement in space exploration. The study of interstellar objects also raises profound questions about the prevalence of planetary systems throughout our galaxy. If objects are being ejected from stellar systems in sufficient numbers to provide the population we observe, then planet formation must be a remarkably common process throughout the cosmos. This abundance of planetary systems increases the likelihood that some may have developed conditions suitable for life. The chemical diversity observed in interstellar visitors suggests that planetary formation occurs under a wide range of conditions, producing objects with compositions that span the full spectrum of possibilities, from the rocky metallic materials found in terrestrial planets to the icy, volatile, rich substances that characterize comets and outer system objects. This diversity implies that the processes leading to planet formation are robust and adaptable, operating successfully across different stellar environments. The preservation of complex organic chemistry in objects like Atlas also has profound implications for astrobiology. If sophisticated carbon-based molecules can survive the harsh conditions of interstellar space for billions of years, then the chemical building blocks of life may be far more widespread throughout the galaxy than previously imagined. These wandering objects could serve as delivery mechanisms distributing biological precursors between stellar systems. The concept of panspermia, the idea that life or its chemical precursors might spread between worlds through natural processes, takes on new relevance in light of interstellar object discoveries. While the survival of actual living organisms during million-year journeys through space remains highly unlikely, the preservation of complex organic molecules provides a more plausible mechanism for sharing biological chemistry between different planetary systems. Each interstellar visitor we study adds another data point to our understanding of how common various chemical processes might be throughout the galaxy. The detection of similar organic compounds in objects from different stellar environments would suggest that the pathways leading to biological complexity are universal features of cosmic chemistry operating consistently regardless of local conditions. The temporal aspect of interstellar object studies provides another unique perspective on galactic evolution. Objects like Atlas, with their ancient origins, serve as archaeological specimens preserving chemical and physical information from epochs in our galaxy's history that cannot be studied through any other means. The composition of these time travelers reveals conditions that existed billions of years ago when stellar formation rates were higher and the chemical composition of the interstellar medium was fundamentally different. By studying visitors of different ages, astronomers can begin to trace how the galaxy's chemical evolution has proceeded over cosmic time. Objects from the thick disk, like Atlas, represent one extreme carrying materials from when heavy elements were scarce, while future discoveries of objects from younger stellar populations will fill in the intermediate stages of this evolutionary timeline. The isotopic signatures preserved in these ancient materials provide particularly powerful tools for understanding galactic chemical evolution. Different stellar processes produce distinctive ratios of isotopes, and these signatures remain frozen in the materials ejected from planetary systems. By measuring isotopic ratios in interstellar objects, astronomers can identify the types of stars that contributed materials to different regions of the galaxy at different times. This isotopic archaeology becomes even more powerful when combined with observations of stellar populations in various galactic regions. By correlating the chemical signatures of interstellar objects with the properties of stars in their likely birth environments, astronomers can begin to understand how stellar mass metallicity and age influence the types of materials available for planetary formation. The extreme orbital characteristics of objects like Atlas also provide insights into the violent processes that can disrupt planetary systems. The tremendous velocities achieved by these objects require gravitational encounters of extraordinary intensity, perhaps close approaches to massive stars or passage through regions where multiple stellar systems are interacting simultaneously. These ejection events represent some of the most dramatic moments in a planetary system's evolution, when the delicate gravitational balance that maintains stable orbits is suddenly disrupted by external forces. The survival of objects like Atlas through such violent encounters, while retaining their volatile materials, speaks to the remarkable resilience of these cosmic wanderers. The study of ejection mechanisms through interstellar objects also informs models of planetary system evolution. Computer simulations suggest that most systems experience periods of instability during their formation when massive planets migrate inward or outward, disrupting the orbits of smaller bodies and sending countless objects into interstellar space. Our own solar system likely underwent such chaotic periods during its youth, with evidence suggesting that the giant planets migrated significantly from their original positions during the first few 100 million years after formation. This migration would have scattered objects throughout the outer solar system and beyond, contributing our own population of wanderers to the galactic community of interstellar travelers. The realization that planetary systems throughout the galaxy are constantly exchanging materials through these ejection and capture processes fundamentally changes how we think about cosmic evolution, rather than isolated islands of matter. Developing independently stellar systems appear to be nodes in a vast network of material exchange operating over billions of years. This cosmic recycling operates on timescales so vast that objects ejected during our galaxy's youth are only now arriving in stellar systems that formed much later, carrying with them chemical information about conditions that existed when the universe was fundamentally different. The materials within Atlas may preserve signatures from stellar nucleosynthesis processes that operated when the galaxy contained far fewer heavy elements than today. The detection and characterization of interstellar objects represents a new frontier in comparative planetology. By sampling materials from diverse stellar environments, we can begin to understand how different conditions affect the outcomes of planetary formation. The composition of Atlas tells us about processes that operated under the metal-poor conditions of the early galaxy, while future discoveries from younger systems will reveal how planetary formation has evolved as heavy element abundances have increased. This comparative approach becomes particularly powerful when we can identify the stellar origins of specific interstellar objects, linking their compositions directly to observable properties of their parent stars. Such connections would provide unprecedented insights into the relationship between stellar characteristics and the types of materials available for planetary formation. The challenges of making such connections highlight the importance of continued advances in both detection capabilities and analysis techniques. As our ability to discover and study interstellar objects improves, we move closer to the goal of creating a comprehensive catalogue that spans the full range of stellar environments represented in our galactic neighbourhood. The upcoming era of survey astronomy promises to transform interstellar object research from a field focused on individual discoveries to one capable of statistical analysis of entire populations, the Vera Rubin Observatory. When it begins, operations will scan the entire visible sky every few nights, providing unprecedented opportunities to detect fast-moving objects that might otherwise escape notice. This systematic approach to sky monitoring will reveal not just more interstellar objects, but also their statistical properties, allowing astronomers to address fundamental questions about the frequency of ejection events, the typical sizes and compositions of wandering objects, and the relationship between stellar system properties and their ejected materials. The coordination required for follow-up observations of newly discovered interstellar objects drives innovation in astronomical communication and data sharing systems. When a potential interstellar visitor is detected, Observatories around the world must be notified immediately to begin the coordinated observations needed to confirm its nature and extract maximum scientific value from its brief passage. This global coordination becomes even more critical as detection rates increase with multiple interstellar objects potentially visible simultaneously. The astronomical community must develop sophisticated prioritization schemes and automated scheduling systems to ensure that observational resources are allocated efficiently to maximize scientific return. The development of artificial intelligence and machine learning techniques specifically designed for interstellar object research represents another frontier in this rapidly evolving field. Automated systems that can rapidly analyze spectroscopic data to identify unusual compositions or detect subtle patterns in brightness variations could dramatically increase our ability to extract information from these fleeting visitors. The integration of multiple data sources, including ground-based observations, space-based measurements, and laboratory analysis of meteorite samples that may have interstellar origins, creates opportunities for comprehensive studies that combine direct observation with detailed laboratory investigation. This multi-platform approach maximizes the scientific return from each discovery while building a comprehensive database of interstellar object properties. The implications of interstellar object research extend far beyond astronomy into fields including planetary science, astrobiology, and even philosophy. The discovery that our solar system regularly receives visitors from other stellar systems fundamentally changes our perspective on our place in the galaxy. We are not isolated, but connected to a vast community of worlds through these ancient messengers. The study of these cosmic time capsules also raises profound questions about the nature of exploration and discovery. In an age when interstellar travel remains beyond our technological capabilities, interstellar objects provide our only direct access to materials from other star systems, bringing alien worlds to us, rather than requiring us to journey to them. Each new discovery adds another piece to the grand puzzle of cosmic evolution, from the chemical signatures that reveal stellar nucleosynthesis processes to the physical characteristics that constrain models of planetary formation. These wandering ambassadors carry within their ancient structures the keys to understanding how the universe creates the conditions necessary for complexity and perhaps even life. The preservation of sophisticated chemistry in objects that have wandered through interstellar space for millions or billions of years suggests that the building blocks of complexity are more robust and widespread than we might have imagined. The harsh radiation environment and extreme cold of interstellar space, rather than destroying complex molecules, may actually serve to preserve them, creating a galactic reservoir of chemical diversity that can seed new worlds with the materials needed for evolution. As we continue to refine our techniques for detecting and studying these visitors, we stand at the beginning of a new chapter in our understanding of the cosmos. The secrets locked within ancient wanderers like Atlas represent just the first glimpses of what promises to be a rich tapestry of discovery, revealing the intricate connections that link all stellar systems in our galaxy through the endless dance of cosmic chemistry and gravitational dynamics. The journey that began with Oumuamua's puzzling behavior and continued through Borisov's familiar yet exotic nature has now reached new heights with Atlas' extreme characteristics and ancient origins. Each discovery has not only answered questions about these specific objects, but has also revealed the existence of entirely new categories of phenomena that we never suspected existed. The story of interstellar visitors is far from complete, with each new detection raising as many questions as it answers about the processes that create, eject, and preserve these cosmic wanderers. As our observational capabilities continue to improve and our theoretical understanding deepens, we can expect these mysterious messengers from the deep to continue surprising us with revelations about the nature of planetary systems throughout our galaxy. The patient work of astronomers, scanning the skies night after night, watching for the subtle movements that betray the presence of another visitor from the stars, continues with the knowledge that each new discovery has the potential to revolutionize our understanding of how the universe operates on the grandest scales. The next interstellar object may already be approaching, carrying within its ancient structure secrets that will reshape our view of cosmic evolution and our place within the vast community of worlds that populate our galaxy. The implications of these discoveries ripple outward like waves across the cosmic pond, touching every aspect of how we understand our galactic neighborhood and our place within it. When we first glimpsed Oumuamua tumbling through our solar system, we thought we were witnessing a rare anomaly, a cosmic lottery ticket that had somehow found its way to our doorstep. But now, with Borisov confirming that interstellar comets behave much as we expected, and Atlas pushing the boundaries of age, velocity, and composition, we begin to realize that we're not observers of isolated events, but witnesses to a fundamental process that has been operating throughout the galaxy's history. The mathematics alone are staggering if current estimates prove correct. Our solar system exists within a sea of wandering objects so vast that it challenges comprehension at any given moment. Thousands of these ancient travelers may be drifting through the space beyond Neptune, invisible to our instruments, but present nonetheless, each one carrying its own story of ejection survival and cosmic wandering. This population represents a kind of galactic memory bank where the history of stellar formation and planetary evolution is preserved in countless frozen archives, drifting silently through the dark. Consider what this means for our understanding of cosmic connectivity. We once imagined stellar systems as isolated islands of matter, separated by vast gulfs of empty space. But the reality appears far more dynamic, with constant exchange of materials between systems through these ejection and capture processes over cosmic timescales. This exchange operates like a vast recycling program, where the failed experiments of one stellar system become the raw materials for discoveries in another. The chemical diversity we observe in these visitors hints at the extraordinary range of conditions under which planetary formation occurs throughout our galaxy. Some objects, like Borisov, carry compositions remarkably similar to our own solar system's comets, suggesting that certain formation processes may be universal. Others, like Atlas, with its extreme age and unique characteristics, represent environments so different from our own that they challenge our theoretical models of how planetary systems assemble and evolve. This diversity becomes particularly intriguing when we consider the implications for habitability. If planetary formation occurs under such a wide range of conditions, producing objects with compositions spanning the full spectrum from rocky metallic materials to complex organic-rich substances, then the environment suitable for the emergence of life may be far more varied than our Earth-centric perspective might suggest. The organic compounds detected in these wandering objects raise particularly profound questions about the distribution of life's building blocks throughout the galaxy. The preservation of complex carbon chemistry in materials that have been exposed to the harsh radiation environment of interstellar space for millions of years suggests that these molecules are far more robust than we might have expected, rather than being destroyed by cosmic rays and ultraviolet radiation. These compounds appear to survive and perhaps even evolve during their long journeys between stars. Some theoretical models propose that the radiation environment of interstellar space, rather than destroying organic molecules, might actually drive the formation of increasingly complex compounds through a kind of cosmic chemistry laboratory operating over geological timescales. If this proves correct, then the space between stars, far from being a sterile void, becomes an active participant in the chemical evolution that may ultimately lead to biological complexity. The concept takes on even greater significance when we consider the delivery mechanisms these objects represent. Every planetary system throughout the galaxy likely experiences bombardment by interstellar visitors carrying chemical cargo from distant stellar environments. This bombardment could serve as a mechanism for seeding worlds with molecular diversity that might not arise locally, ensuring that the building blocks of complexity are distributed widely throughout the cosmos. The timing of such deliveries becomes crucial for understanding how life might emerge on different worlds. Objects arriving during a planet's formation phase, when surfaces are still molten, would have their organic inventory destroyed by extreme temperatures. But those arriving later after conditions have stabilized could deposit their chemical treasures intact, potentially providing the spark needed for biological evolution to begin. The study of current interstellar visitors provides insights into what kinds of chemistry might have been delivered to Earth during its own formation, epoch billions of years ago. Our planet likely received countless impacts from similar objects, each potentially carrying organic compounds and volatile materials from diverse stellar environments. The chemical diversity of life on Earth may owe its origins not just to terrestrial processes, but to this cosmic seeding by materials from throughout our galactic neighborhood. Atlas, with its potentially 7 billion year age, represents a particularly intriguing case study in cosmic preservation. If confirmed, this object would carry within its nucleus chemistry that predates our entire solar system. By billions of years, the conditions under which its organic compounds formed would have been vastly different from those operating today, when heavy elements were scarce and stellar. Nucleosynthesis was still in its infancy. The preservation of such ancient chemistry offers unprecedented opportunities to study molecular evolution across cosmic time. By analyzing the organic inventory of objects with different ages, we could begin to trace how the complexity and diversity of interstellar chemistry has changed as our galaxy has evolved. This temporal sampling becomes even more powerful when combined with observations of stellar populations in different galactic regions. The thick disk region from which Atlas likely originated contains stars with distinctly different properties than those found in our Sun's neighborhood. These ancient stellar populations formed when the galaxy was metal-poor, containing much lower abundances of the heavy elements crucial for rocky planet formation. Studying objects from such environments reveals how planetary formation proceeds under these different chemical conditions. The size estimates for Atlas ranging from a few kilometers to potentially over 40 kilometers in diameter highlight another fundamental aspect of these discoveries. If the larger estimates prove correct, Atlas would represent a completely different class of interstellar object than the relatively small bodies we have previously encountered. Large objects would have different survival characteristics during their wandering journeys, their greater gravitational binding making them more resistant to tidal disruption, while their larger surface area would make them more susceptible to erosion processes. The discovery of genuinely massive interstellar objects would also have implications for understanding the ejection mechanisms that send these wanderers on their cosmic journeys. Launching a large object to the velocities needed for interstellar escape requires tremendous gravitational interactions, perhaps close encounters with massive stars, or passage through regions where multiple stellar systems are gravitationally interacting. The extreme velocity of Atlas, over 130,000 miles per hour, sets new records for interstellar objects and provides clues about the violent processes that launched it from its birth system. Such tremendous speeds require gravitational encounters of extraordinary intensity, the kind of chaotic dynamics that might occur during the formation of binary star systems or the disruption of planetary systems by passing stars. These high-velocity encounters with the tenuous interstellar medium during Atlas' long journey would have created a kind of cosmic sand-blasting effect, gradually eroding surface materials and potentially exposing deeper layers. This process might explain some of the evolving spectral characteristics observed as the object approaches our Sun, with each eroded layer revealing different aspects of its ancient composition. The detection of objects moving at such extreme velocities also pushes our observational capabilities to their limits. Tracking something racing through space at over 130,000 miles per hour requires extraordinarily precise measurements and rapid telescope response times. The brief observational windows available before such objects disappear back into interstellar space demand unprecedented coordination between observatories worldwide. The development of automated detection systems specifically designed to identify fast-moving objects represents a crucial advancement in our ability to study these visitors. The Atlas survey that discovered our most recent wanderer exemplifies this new generation of sky monitoring systems capable of processing vast amounts of data in real time to identify objects with unusual motions or characteristics. This technological evolution promises to transform interstellar object research from a field focused on rare individual discoveries to one capable of statistical analysis of entire populations. The Vera Rubin Observatory. When it begins, operations will provide unprecedented systematic coverage of the sky, detecting potentially hundreds of interstellar objects during its operational lifetime. Such a dramatic increase in detection rates will enable entirely new approaches to understanding these cosmic wanderers rather than analyzing isolated specimens. We will be able to study population statistics, examining the relationships between object size, composition, velocity, and stellar origin. This statistical approach will reveal patterns invisible in individual case studies. The coordination required for follow-up observations of newly discovered interstellar objects has already driven innovation in astronomical communication and data sharing. When Atlas was first detected, observatories around the world mobilized within hours, demonstrating the kind of rapid response capability needed to maximize scientific return from these fleeting opportunities. This global collaboration transcends traditional boundaries in astronomy. These visitors belong to no single nation or institution. They are messengers from the galaxy itself, requiring the combined efforts of the entire astronomical community to unlock their secrets. The free flow of data between observatories reflects the universal nature of the scientific questions these objects raise. The international cooperation fostered by interstellar object research provides a model for addressing the grand challenges that face astronomy in the coming decades. As we develop increasingly sophisticated instruments and undertake more ambitious projects, the collaborative frameworks established for studying these visitors will prove invaluable for tackling questions that require resources and expertise from around the globe. The technological demands of studying these objects continue to drive innovation across multiple fields, from detector technologies that can capture more photons in shorter exposure times to adaptive optic systems that maintain sharp focus on rapidly moving targets. Each advance in capability opens new possibilities for extracting information from these brief encounters. The development of space-based observatories specifically designed for interstellar object research represents the next frontier in this rapidly evolving field. Telescopes positioned beyond Earth's atmosphere can observe these visitors across the full electromagnetic spectrum without atmospheric interference, while their stable platforms enable the long-duration tracking needed to follow objects across their entire passage through the inner solar system. The James Webb Space Telescope has already begun contributing to interstellar object studies with its unprecedented infrared sensitivity, revealing thermal characteristics and composition details invisible to ground-based instruments. Future dedicated missions may attempt even more ambitious goals, including spacecraft intercepts that could provide direct samples of interstellar materials. The concept of intercepting an interstellar object presents extraordinary technical challenges. These visitors approach with such high velocities that matching their speed and trajectory pushes propulsion capabilities to their limits. Yet the scientific rewards would be immense, providing actual samples from another star system for detailed laboratory analysis. Several mission concepts have been proposed, ranging from high-speed flyby encounters to more ambitious rendezvous attempts that would pace alongside an interstellar visitor for extended observation periods. The engineering challenges are formidable, but represent the kind of ambitious goals that drive technological advancement in space exploration. The study of interstellar objects also raises profound philosophical questions about exploration and discovery in an era when interstellar travel remains beyond our reach. These cosmic visitors provide our only direct access to materials from other star systems, bringing alien worlds to us rather than requiring us to journey to them. Each object represents a kind of natural space mission, launched not by intelligent design, but by the chaotic gravitational dynamics that govern stellar system evolution. These accidental ambassadors carry within their structures information about worlds and processes we may never be able to study through any other means. The chemical signatures preserved in these ancient wanderers serve as a form of cosmic archaeology, revealing conditions that existed in distant stellar systems during epochs we cannot observe directly. The isotopic ratios, organic compounds, and mineral compositions found in interstellar objects provide direct samples of the materials from which other worlds were built. This archaeological perspective becomes particularly powerful when applied to objects of different ages by comparing the chemistry preserved in ancient visitors like Atlas. With that found in younger objects, we can begin to trace how stellar nucleosynthesis and chemical evolution have proceeded throughout our galaxy's history. The preservation of complex organic molecules in these objects, despite their exposure to harsh radiation environments for millions of years, suggests that the chemistry of life may be more robust and widespread than previously imagined, rather than being fragile accidents confined to the surfaces of habitable worlds. These compounds appear capable of surviving and perhaps evolving during extended journeys through interstellar space. This robustness has profound implications for astrobiology. If the building blocks of biological complexity can survive interstellar transport, then the chemical prerequisites for life may be distributed throughout the galaxy by these wandering carriers, seeding new worlds with molecular diversity that enhances their potential for developing complex chemistry, and perhaps eventually life itself. The concept of chemical seeding through interstellar objects provides a mechanism for understanding how the ingredients necessary for biological evolution might become available in stellar systems where local conditions alone would not produce such complexity. This process could help explain the rapid emergence of life on Earth and suggest that similar developments might be common throughout the galaxy. The detection of water ice in objects like Atlas, despite their extreme age and long exposure to space conditions, demonstrates the remarkable preservational power of the cosmic deep freeze. Temperatures in interstellar space hover just degrees above absolute zero, cold enough to maintain even volatile materials in stable crystalline forms for geological timescales. When this ancient ice begins to sublime as objects approach our sun, it releases not just water vapor, but complex mixtures of gases that were trapped during the original freezing process. These trapped volatiles serve as time capsules, preserving atmospheric signatures from the stellar systems where these objects formed billions of years ago. The analysis of these released gases provides direct insights into the conditions that existed in distant planetary systems during their formation. Epochs revealing information about temperature, pressure, and chemical processes that operated under vastly different circumstances than those we observe in our own solar system today. The isotopic signatures found in these materials offer particularly powerful tools for understanding stellar nucleosynthesis and galactic chemical evolution. Different types of stars produce distinctive isotopic ratios, and these signatures remain frozen in ejected materials for billions of years. By measuring isotopic compositions in interstellar objects, we can identify the stellar sources that contributed materials to different regions of the galaxy at different times. This isotopic archaeology becomes even more revealing when combined with observations of current stellar populations. By correlating the chemical signatures found in ancient visitors with the properties of stars in their likely regions of origin, we develop a comprehensive picture of how stellar evolution has shaped the chemical landscape of our galactic neighborhood. The extreme orbital characteristics that define these objects as interstellar also provide crucial information about the ejection processes that launched them from their birth systems. The hyperbolic trajectories and high velocities observed in objects like Atlas require gravitational encounters of tremendous intensity, far exceeding anything commonly experienced within stable planetary systems. These violent ejection events represent critical moments in planetary system evolution, when the delicate gravitational balance maintaining stable orbits is suddenly disrupted by external forces. The fact that objects survive such encounters while preserving their internal structure and volatile materials speaks to either remarkable resilience or fortunate circumstances that allowed them to escape relatively intact. Computer simulations of planetary system formation suggest that such ejection events are not rare accidents, but fundamental aspects of how stellar systems evolve. Most simulations indicate that far more objects are ejected into interstellar space than are retained in stable orbits, with ratios ranging from 3 to 100 ejected objects for every one that remains bound to its parent star. This implies that the interstellar medium contains a vast population of these wandering remnants, representing the collective debris from planetary formation processes throughout the galaxy's history. The objects we detect represent only the tiniest fraction of this population, limited by our current observational capabilities to the largest and most active specimens. The hidden population of smaller inactive interstellar objects may dwarf the numbers we currently observe by factors of millions or billions, creating an invisible diaspora of materials constantly flowing between stellar systems. This continuous exchange represents a form of galactic recycling, where the products of stellar evolution in one system become available as raw materials for planet formation in others. The realization that planetary systems throughout the galaxy are connected through these material exchange processes fundamentally changes our perspective on cosmic evolution, rather than developing in isolation. Each stellar system participates in a vast network of chemical and physical exchange operating over billions of years. This connectivity has profound implications for understanding how complexity and potentially life might emerge and spread throughout the galaxy if the chemical building blocks necessary for biological evolution can be transported between systems by interstellar objects. Then the development of life becomes not just a local phenomenon, but part of a galaxy-wide process of chemical and biological evolution. The study of these cosmic time travelers also provides unique insights into the long-term stability of complex systems under extreme conditions, the survival of delicate organic molecules and crystalline ice structures during million-year journeys through the harsh radiation environment of interstellar space, demonstrates that complexity can persist under conditions far more severe than those found on planetary surfaces. This persistence suggests that the universe may be far more hospitable to complex chemistry than we might expect based solely on the relatively benign conditions found in habitable zones around stars. The space between stars, rather than being a sterile wasteland, appears capable of preserving and perhaps even fostering the chemical complexity that underlies biological processes. The implications extend beyond chemistry to questions of information, storage and transmission. If complex molecular structures can survive interstellar transport, they might serve as carriers of chemical information between stellar systems, providing a mechanism for sharing the products of evolution across vast distances and timescales. Each interstellar visitor we study adds another piece to this grand puzzle, revealing new aspects of how the galaxy operates as an integrated system, where materials, energy, and information flow between stellar systems through processes. We are only beginning to understand the ancient wanderers drifting through our solar system represent far more than curious astronomical specimens. They are active participants in cosmic evolution, carrying within their structures the accumulated wisdom of billions of years of stellar and planetary development. As our detection capabilities continue to improve, and our analytical techniques become more sophisticated, we can expect these mysterious messengers to continue surprising us with revelations about the nature of planetary systems throughout the galaxy. The secrets locked within their ancient structures represent keys to understanding not just the history of our cosmic neighborhood, but the fundamental processes that shape worlds and perhaps life itself throughout the universe. The patient work of scanning the skies for these subtle visitors continues, with each new detection potentially revolutionary in its implications for our understanding of cosmic evolution. The next interstellar object may already be approaching our solar system, carrying within its frozen nuclear secrets that will reshape our comprehension of how the universe creates the conditions necessary for complexity, beauty, and perhaps even consciousness to emerge from the cosmic dark. The story of these wandering ambassadors from distant stars reminds us that we are part of something far grander than our small corner of the cosmos might suggest. Every night, as we look up at the familiar constellations, we share the sky with countless invisible travelers, each one carrying within its ancient heart the chemical memories of worlds beyond imagination. Perhaps the most humbling realization is that these objects had been making their silent pilgrimages long before our sun began to shine, before the Earth coalesced from cosmic dust, before life took its first tentative steps in primordial oceans. Atlas, with its 7 billion-year heritage, has witnessed the birth and death of countless stars, has drifted through regions of space where galaxies themselves were young, and the very elements that make up our bodies were still being forged in stellar furnaces. There is something profoundly moving about the thought that as you sit here tonight, listening to these words, molecules within your own body may once have been part of similar wandering objects that arrived at Earth during its formation. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of every protein may have traveled for eons through the cosmic dark before finding its way into the materials that eventually became you. This cosmic recycling operates on scales that dwarf human comprehension. Yet it connects us intimately to the broader universe. We are not separate from the cosmos, but woven into its very fabric through processes that span billions of years and countless light years. Our existence depends on this ancient dance of creation, destruction and renewal that plays out across the galaxy. The organic compounds detected in these interstellar visitors tell a particularly compelling story about the universality of the chemistry that underlies life. The fact that complex carbon molecules can survive million-year journeys through space suggests that the building blocks of biological complexity may be far more common and resilient than we ever dared hope. Imagine the implications. If these wandering laboratories are constantly experimenting with new molecular combinations driven by the gentle but persistent influence of cosmic radiation, creating ever more sophisticated chemistry during their long voyages between stars, the space between worlds, rather than being empty, becomes a vast research facility where nature conducts experiments on timescales we can barely comprehend. The preservation of water ice in objects that have wandered for billions of years speaks to the remarkable ability of the universe to maintain the conditions necessary for complexity, even in the apparent harshness of interstellar space. That ancient ice, when it finally sublimates, near our sun releases vapors that may contain the atmospheric signatures of worlds that vanished long before our solar system existed. There is poetry in the thought that the steam rising from your evening tea might contain water molecules that once formed clouds on alien worlds that orbited stars whose light has long since faded from the sky. The boundaries between here and there, between now and then, become beautifully blurred when we consider the deep connections that link all matter in the universe. The extreme velocities of objects like Atlas racing through our solar system, at speeds that challenge our ability to track them, remind us of the tremendous energies involved in cosmic evolution. The gravitational encounters that launch these objects on their interstellar journeys represent some of the most violent events that can occur in planetary systems. Yet from destruction comes discovery, from chaos comes the opportunity for new understanding. These cosmic catastrophes that scatter objects across the galaxy also serve as distribution mechanisms, ensuring that no stellar system develops in complete isolation. The materials ejected from one world become the seeds for discoveries in another, creating a vast network of chemical and physical exchange that operates throughout the galaxy. The technological challenges of studying these fleeting visitors continue to push the boundaries of what is possible in astronomical observation. The coordination required when a new interstellar object is detected, the rapid mobilization of telescopes around the world, the sophisticated analysis techniques needed to extract maximum information from brief encounters, all represent humanity at its collaborative best. There is something deeply hopeful about watching the global astronomical community come together to study these visitors. The free sharing of data, the coordination of observations across continents, the collective effort to understand what these objects can teach us about the universe, demonstrates that curiosity and wonder can transcend all the divisions that too often separate us. The future promises even more remarkable discoveries. As our detection capabilities continue to improve, the Vera Rubin Observatory will soon begin its systematic survey of the sky, potentially discovering hundreds of interstellar objects and transforming our understanding from isolated case studies to comprehensive statistical analysis of entire populations. Imagine what we might learn when we can compare the compositions of dozens or hundreds of these visitors, examining how the chemistry of ejected materials varies with the age and type of their parent stars, tracing the evolution of planetary formation processes across cosmic time, understanding the full diversity of worlds that exist throughout our galactic neighborhood. The possibility of spacecraft missions to intercept these objects, while technically challenging, represents one of the most exciting frontiers in space exploration. The idea of actually sampling materials from another star system, of bringing alien matter back to Earth for detailed laboratory analysis, captures the imagination in ways that few scientific endeavors can match. Even if such missions remain decades in the future, the very fact that we can contemplate them speaks to the remarkable progress we have made in understanding and exploring the cosmos, from the first tentative steps beyond our atmosphere to the sophisticated robotic explorers. Now studying distant worlds, we continue to expand the boundaries of human knowledge and capability. The philosophical implications of these discoveries extend far beyond astronomy or planetary science. They touch on fundamental questions about our place in the universe, our connection to the cosmos, and the meaning we derive from understanding our cosmic context. The realization that we live in a galaxy where materials are constantly being exchanged between stellar systems fundamentally changes how we think about isolation and connection. We are not alone in the sense that life may exist elsewhere, though these objects cannot yet answer that question directly. But we are certainly not alone in the sense that our solar system participates in a vast community of worlds, connected through the ancient processes that govern stellar and planetary evolution. The chemical signatures preserved in these wandering time capsules will continue to reveal secrets about the history and evolution of our galaxy. Each new detection adds another piece to the grand puzzle of cosmic development, helping us understand how the universe creates the conditions necessary for complexity and perhaps even consciousness to emerge. The patient work of monitoring the skies for these subtle movements against the stellar background continues night after night as automated telescopes scan vast areas of space, watching for the telltale signs that might indicate another messenger approaching from the deep. The next discovery could come at any moment, carrying with it revelations that reshape our understanding of cosmic evolution. There is something beautifully democratic about these discoveries. The objects themselves choose when and how to reveal themselves to us, arriving unannounced from the darkness to grace us with their presence for brief moments before continuing their eternal wandering through the galaxy. We cannot summon them or schedule their arrivals. We can only remain vigilant and ready to learn from whatever gifts they choose to bring. As detection rates increase with new survey systems coming online, we may soon find ourselves in the remarkable position of having multiple interstellar visitors simultaneously gracing our solar system, each one offering its own unique perspective on the processes that shape worlds throughout the galaxy. The richness of this future database will enable studies we can barely imagine. Today, the story of Oumuamua. Borisov and Atlas represents just the opening chapter in what promises to be a long and fascinating book of discovery. Each page will reveal new aspects of how the galaxy operates as an integrated system where the products of stellar evolution flow between worlds, carrying information about the diversity of processes that create and sustain planetary systems. The ancient wanderers drifting through our cosmic neighborhood are far more than curiosities or astronomical specimens. They are active participants in the ongoing evolution of the galaxy, messengers carrying news from distant realms, and time travelers preserving the chemical memories of epochs. We cannot observe directly in their tumbling journey through space. They embody the fundamental interconnectedness that characterizes the universe on the largest scales. Nothing exists in isolation. Everything participates in the vast dance of creation and evolution. that has been unfolding for billions of years and will continue for billions more. The organic molecules preserved in these objects whisper of possibilities that extend far beyond their immediate chemical significance if life is indeed a cosmic phenomenon rather than a terrestrial accident. Then these wandering carriers of biological building blocks may play crucial roles in seeding new worlds with the molecular diversity necessary for evolution to begin, whether or not we ever detect clear evidence of life beyond Earth. The study of these interstellar visitors enriches our understanding of the conditions that make complexity possible throughout the universe. They demonstrate that the chemistry underlying biological processes operates under a far wider range of conditions than we might have expected, based solely on terrestrial experience. The preservation of delicate structures across million-year journeys through space reveals that the universe is far more hospitable to complexity than the apparent harshness of interstellar conditions might suggest. The cosmic dark, rather than being destructive, serves as a preservative medium, maintaining ancient chemistry in pristine condition across vast distances and timescales. Each measurement, each spectrum, each carefully tracked trajectory adds to our growing appreciation of the remarkable processes that operate throughout the galaxy. The universe reveals itself to be not a collection of isolated worlds, but a vast interconnected system where matter, energy, and information flow freely between stellar systems through mechanisms we are only beginning to understand. The next clear night, when you step outside and look up at the stars, remember that you are witnessing far more than a static display of distant lights. You are observing a dynamic system where countless unseen travelers are making their silent way between worlds, carrying with them the accumulated wisdom of billions of years of cosmic evolution. Somewhere in that darkness, another ancient wanderer may already be approaching our solar system, racing toward us at tremendous speed, with a cargo of secrets that will challenge everything we think we know about how worlds form and evolve. The patient telescopes continue their vigil, ready to sound the alert when the next messenger from the deep reveals itself against the stellar background. The story of these cosmic time travelers reminds us that we live in a universe far stranger and more wonderful than our everyday experience might suggest. The familiar rhythm of days and seasons, the predictable dance of planets in our sky, mask the deeper currents of change and exchange that operate on scales spanning the entire galaxy. In the gentle rotation of these ancient objects as they tumble through our solar system, we glimpse something of the vast choreography that governs cosmic evolution. Each spin, each subtle change in brightness tells part of the story of violent ejection and patient wandering of survival against tremendous odds and eventual discovery by minds curious enough to wonder about their origins. The mathematics that describe their hyperbolic trajectories speak of energies and processes that dwarf anything we experience on Earth. Yet these same equations reveal the underlying order that governs even the most chaotic events in cosmic evolution. Beauty emerges from violence, stability from disruption and knowledge, from the patient observation of phenomena that initially appear alien and incomprehensible. As we continue to refine our understanding of these visitors, we participate in one of the most fundamental activities that define us as conscious beings. The drive to understand our place in the cosmos, to make sense of the phenomena we observe, and to find meaning in the vast scales of space and time that surround us. The ancient wanderers carry within their frozen hearts not just the chemistry of distant worlds, but also the potential for new understanding, new perspectives on what it means to exist as thinking beings in a universe that seems designed to surprise us with its complexity and beauty at every turn tonight as you drift towards sleep. Perhaps you will dream of these cosmic travelers making their way through the darkness between stars, carrying their precious cargo of ancient chemistry and timeless secrets through the vast ocean of space that connects all worlds in the endless dance of cosmic evolution. And so, dear fellow stargazers, we reach the end of our cosmic journey through the realm of interstellar visitors. Those remarkable wanderers that have drifted across unimaginable distances to share their ancient secrets with us tonight. We've witnessed the universe revealing itself as far stranger and more interconnected than we ever dared imagine, from Oumuamua's puzzling acceleration that first challenged our understanding to Borisov's familiar yet exotic chemistry that provided reassuring confirmation of our theories, and finally, to Atlas with its extreme velocity, ancient origins, and potentially billion-year-old secrets. We've seen how each visitor has expanded our knowledge while raising entirely new questions about the nature of these cosmic nomads. These three extraordinary objects represent just the beginning of what promises to be a golden age of interstellar visitor research. As new telescopes come online and detection rates increase, we stand on the threshold of transforming these rare curiosities into a regular part of astronomical study, enabling us to map the chemical evolution of our galaxy through direct sampling of materials from distant stellar systems. The realization that we exist within a vast sea of wandering objects, constantly exchanging materials between star systems, fundamentally changes our perspective on cosmic evolution. We are not isolated observers, but active participants in a galactic community connected through processes that operate across billions of years and countless light years. Tonight, somewhere in the darkness beyond our solar system, another ancient messenger may already be racing toward us, carrying within its frozen nucleus chemistry from worlds we can never visit directly. The patient telescopes continue their vigil, ready to alert us when the next visitor reveals itself against the stellar background. If this exploration into the mysteries of our cosmic visitors has brought you wonder or perhaps helped ease you toward peaceful dreams, I'd be deeply grateful if you could give this video a like and subscribe. It helps ensure that others who find solace in contemplating the vastness above might discover this little corner of cosmic curiosity. Sleep well, fellow travelers, and remember that even as you rest, the ancient wanderers continue their eternal journey through the galaxy, carrying with them the accumulated wisdom of billions of years of stellar evolution and the promise of discoveries yet to come.